All right, welcome everyone to Additive Manufacturing Friday. Today we have Adam Parsons and Nick Martin, who are both engineers here at Markforged, and they're going to talk about high-strength 3D printing filaments. Whenever you guys are ready, kick us off.
Great, thanks Marco for the intro. As Marco said, I'm Nick.
And I'm Adam, nice to meet you guys.
And so over the past few episodes of AM Fridays, we've been talking a lot about metal. Last week was more specifically about metal materials. And we talked a little bit about the cost volume curve of metal 3D printing. And so this episode, we're going to kind of transition a little more towards the plastics and composite side and talk about high strength 3D printing filaments. And so I think a good way to get into this is to think about where 3D printing really came from in the beginning and how that informs how we've progressed through towards these more high strength materials. So Adam, if you want to speak a little to that.
Yeah, so I mean, those of you that are familiar or aren't, quick little history lesson is if we go back to, I think it was 1984, Chuck Hull with 3D Systems was the first one to patent stereolithography, which is what a lot of 3D printers still use today for at least a file type of STLs. That kind of led to SLA printing and high resolution printing that we know it as today, but it wasn't always that way. Mm-hmm. Kind of plastics had to evolve. It wasn't really until 2005 with kind of the RepRap project movement where hobbyists, people using additive were basically making their own printers, printing their own parts with their printers to improve their print quality, which has kind of led us to the last decade worth of improvements in plastics where now we're less focused on hardware capabilities and quality, and now we're starting to look at different material properties and the limitations of those as they relate to applications. So really starting to dive in on what plastics are available today from an engineering standpoint, what the advantages of one over the other are. And so hopefully today we can kind of just talk through some of those and cover where we kind of fit to the mix, as well as what other plastics are available for additive today.
Certainly. And if you're familiar with 3D printing and you've used some desktop 3D printers in the past, odds are you're typically printing in materials like ABS and PLA, two of the most popular filaments out there. And those do have some good qualities in the fact that they're very inexpensive. You can get them for like $20 a spool. And they're really good for tinkering and for making quick 3D objects. There is something to be said about those thermoplastics that aren't necessarily high performance engineering materials, but really were the foundation of 3D printing from the beginning in an accessibility standpoint. And so now, as Adam mentioned, through not just 3D printing, R&D, but also different materials research, we've gotten to the point where we're printing these really high strength materials. So for example, one material that's kind of been buzzing a lot recently is PEEK and also Ultem, which is really similar to PEEK. And so this is kind of the cream of the crop when it comes to like engineering thermoplastics, not necessarily only with 3D printing, but just in the thermoplastic industry in general. It's a plastic that has really, really high heat resistance. And so its heat deflection temperature is around 215 degrees Celsius. For all you Fahrenheit people out there, it's like about 420 degrees Fahrenheit. And so you're seeing that you can use this plastic in those really high heat applications. And also it's really wear resistant and has really high strength. So it's like when we talk more about like filled thermoplastics and mixed thermoplastics later on that start to involve carbon fiber, it's like up there with that sort of strength. And so, but it has its downsides. So if you're printing in PEEK and Ultem, you get these really good high temperature properties, but as a result, you have to print it at an extremely high temperature. We're talking nozzle temperatures of like 400 degrees Celsius or 750 Fahrenheit, which is pretty difficult to achieve. And then you also need a heated bed at about 120 Celsius. And so keeping a uniform temperature across a part as you print in PEEK and Ultem is something that is necessary to keep warping from happening, but also very difficult because you have this box filled with air and keeping a uniform temperature throughout that is something that's hard to do. And so this makes the process very expensive. You need these controlled industrial environments to print in these materials, which makes it makes a little less sense to choose it as a 3D printing material once you have that barrier to entry.
Yeah, I'd say the accessibility is probably the biggest thing that's hard to overcome with PEEK and Ultem, right? So that cost point to get the quality or specific material characteristics is what prevents a lot more general users from using that as kind of their entry point into additive. Mm-hmm. Kind of similar to PEEK and Ultem is polycarbonate. So polycarbonate is Also a fairly high strength. Probably doesn't quite have the heat deflection temperature range that Peak and Ultim does. It's kind of more in the 130C range. It's insulative to electricity. So oftentimes we're seeing a lot of like telecommunication electronics companies, when they're looking to get into additive, that's kind of a good entry point for them. Sometimes you can also get it in translucent, transparent. So it's good for like lighting applications, things like that. Similar to Peak and Ultim though, it's hard to print. So it requires a heated bed. It requires to have that kind of consistent thermal properties throughout the print, which those of you that are more familiar with ABS and PLA, those are kind of the pains that you're used to of warping off the bed, hold down throughout the print, differential settling as you print in the plastic itself. So that's not inconsistent with polycarbonate as well.
Yeah, and it's interesting, as you mentioned, we're running into very similar challenges even as these materials are progressing. You're printing in PEEK, which is this really high strength, high performing plastic, but you're still getting the issues that people have had for 2 decades trying to print ABS, where you need that heated bed, you're trying to keep it from warping. And so it's like same issue, but just different day, different material, which is something that's really interesting.
Exactly, and that's where I think mixed thermoplastics is really starting to command the market. So it takes the advantages of some of those more kind of commodity plastics of like nylon-based plastics that are easier to print with and are more stable, and allows us to start blending in the strength and stiffness properties that are desired for specific applications. So depending on what reinforcement is being blended in, what fiber itself, whether it's glass, whether it's carbon-based, we're starting to see that these nylon 6, nylon 12 bases are allowing us to have a more stable print, better surface finish, more repeatable, higher tolerance, but much easier to print themselves.
So let's start from the beginning on mixed thermoplastics. So you're mentioning that nylon is really the base thermoplastic in a lot of these. So what is advantageous about printing in nylon, and what are some challenges that may exist in that? And how does that fit into making these mixed thermoplastics as you're talking about?
Yeah, so I'd say probably one of the biggest ones is like chemical resistivity. So we're seeing a lot of different tooling, industrial applications where they're using cooling fixtures, different oils, things like that. Nylon 6 is very resistive to those, and so it's stable. It allows us to not just be kind of printing these prototype parts, but to actually print end-use parts. And so I think that's definitely an advantage. Also from the standpoint of the stability of the plastic matrix itself, nylon 6 is very stable. And so that allows us to have a solid foundation for the part as we're printing. So then when we start talking about different fiber reinforcement, specifically with our technology here at Markforged, then we're less concerned about the print quality or is the print going to succeed, as we are, where are we going to engineer the placement of the specific fiber reinforcement to allow us to kind of proactively respond to the application.
And so the interesting thing is that nylon is actually a pretty weak plastic. It's very flexible, it's pretty durable, but when it comes down to absolute tensile or flexural strength, it actually falls below both PLA and ABS.
Exactly.
But it has properties to leverage, which include, as you say, chemical resistivity, its general printability and nice surface finish, as long as you keep the filament dry. And so then the idea of a mixed thermoplastic is what you're doing. You're taking nylon and then you're mixing in a chopped fiber. So the 2 main ones that we've seen is carbon fiber. So our Onyx material, which you see laid out here, is nylon mixed with chopped carbon fibers, and then there's chopped fiberglass that exists in some filaments as well. And so the idea is to take the good parts of nylon, which are that chemical resistance, its nice surface finish, and its printability. Although it is, maybe a little less printable than like a PLA, and then mixing that with the strength that comes with those chopped carbon fibers to get a part that's really useful in areas that may involve those oils or those chemicals that you're encountering in a factory sort of setting.
Exactly. Yeah, and so that was why us, here at Markforged, as you started kind of allude to, Nick, is a lot of the times we're seeing carbon-based reinforcement or blending into that thermoplastic. We kind of went a step further of developing this even stronger base plastic matrix of kind of a blended thermoplastic that is carbon-based in a nylon 6. And that allows us to have a very strong plastic matrix, as seen in some of these grippers. Stronger than ABS, stiffer, and then transitioning to how can we even leverage that further of introducing, very specific fiber reinforcement. So here we see fiberglass, which then allows us to be kind of very intentional in how we're designing these parts.
Yeah, so to be clear, there's really two things we're talking about here in this sort of part where that Adam showed with the fiberglass. There's that black mixed thermoplastic, which is onyx, which is that nylon 6 mixed with chopped carbon fibers. And then there's these continuous fibers that we've developed as well. So these are really two different things. There's that thermoplastic, and then there's those continuous fibers that you can also reinforce it with.
Right. So depending on the need of the application, sometimes our base thermoplastic onyx is strong enough, it's stiff enough for what you're trying to do. And therefore we can print it faster, it's cheaper, you can get higher value out of just that base plastic matrix. But then if you have specific needs, specific loading conditions that we need to respond to more specifically, then we also offer 4 different varieties of fiber reinforcement. So for us, those are fiberglass, carbon fiber, Kevlar, and high strength, high temperature fiberglass as well, which, we can spend some time and kind of just dig into each of those.
Yeah, and so, but right before we dig into those, so far we've talked about PEEK and Ultim and polycarbonate, and then these mixed thermoplastics. And so in terms of how those all compare to each other from like a strength and stiffness perspective, polycarbonate's really on par with onyx in terms of strength. It's about 40% or so stronger and stiffer than ABS. So not leaps and bounds above it, but it's good progress further. And then PEEK and Ultim, we're seeing stiffness and strength that's higher than both polycarbonate and most mixed thermoplastics. It's the next level from those.
Right.
And so what we're going to talk about now is these continuous fibers, which, as you mentioned, fiberglass, Kevlar, carbon fiber, and then high strength, high temperature fiberglass is that next step past PEEK and Ultim, where you're getting even higher strength, even higher stiffness, and then a kind of a suite of material properties that you can choose from as well.
Sure.
And so I think one that I like to start with is fiberglass, just because as we do, because it doesn't, to be honest, is not the strongest of the 4. But it's a really good place to start because it's got stiffness that's higher than almost every other 3D printing filament out there, and a strength that's higher than PEEK and Ultim, for example.
Right. So, and the benefit with fiberglass is it will bend as it's being flexed. It'll deform, but it won't have kind of the brittle fracture point that carbon fiber does. So carbon fiber is actually much stronger, has a great strength to weight ratio over fiberglass. It's going to be a little bit more expensive to print with, just from a material production standpoint. But when carbon fiber fails, due to that brittle nature, it's going to fracture.
The catastrophic failure.
Right. And so while you get that higher strength ratio, you don't quite have the same flexibility when it comes to the part itself. And kind of similar, if we're talking about the ability to have repeated loading conditions, Kevlar is probably going to exceed both fiberglass and carbon fiber. So that repeated kind of impact, that durability, that ductile range, Kevlar is going to exceed both of those. You may not have the strength that you're going to get with carbon fiber. You may not have the stiffness, but this is where we kind of tailor this conversation depending on the application needs. Those are kind of what we start to consider. And
it's interesting, we talk about Kevlar as, it's not as high strength or stiffness as carbon fiber, but if you compare Kevlar reinforcement in a part to a thermoplastic you're used to working with, like ABS or nylon or something, it's leaps and bounds stronger than that.
Oh, absolutely.
And so it's kind of keep in mind the scale of what we're talking about, which is it's interesting that we have if you should check out our stress strain curve that we have on our material sheet. That's on our website at markforged.com. You can kind of see how it shows the thermoplastics at the bottom, which are very flat curves because they're extremely ductile because they're plastics, and then the fibers, as Adam was saying, the carbon fiber very stiff, and Kevlar has that really, really long plastic deflection range where you're going to see it bend and deform before it fails, which is very useful in certain applications.
Yeah, and we can't forget high strength, high temp, which I know is your personal favorite.
That is probably my favorite fiber, I would have to say. You are not wrong.
Yeah. So I mean, the great part with high strength, high temperature fiberglass is it allows us to be competitive with not quite as high as PEEK and Ultim with a heat deflection temperature range, but now we're starting to talk about things like thermoset molds, things of that sort that have that requirement. for a higher temperature range. Once again, the benefit is by having these 4 different options, you're not kind of locked into these singular material characteristics. This is the true benefit of talking about composites when it comes to plastics, is now we can start to tailor each part to whatever the application needs are.
Yeah, exactly. And so with HSHT fiberglass, for example, you mentioned the high strength or the high temperature, use cases. But an interesting thing about that is it has a very long elastic range of deflection. So with HSHT fiberglass, parts reinforced with that, they're able to deflect a large amount, but then they're able to go back to their original shape. And so that sort of energy storage has interesting implications in how you want to use that as well. For example, if you're like, this is a thermoset mold, for example. Humanetics is one of our customers, and they use this to make this really complex neck ring that goes on crash test dummies. And so this thing has to be clamped shut to ensure that it doesn't flash at all. And so you can clamp it shut and it will deform to the shape that it needs to without letting any leakage happen, any flash happen. But then when you unclamp it, when you unscrew it, you can retain your original shape.
Exactly.
And so that it makes it really good for those molding applications when you're using like molding with different silicons and those sorts of materials.
Sure. Yeah, and I would say, the kind of where we've come, going back to the kind of the history of starting with SLA, these ABS, PLA, kind of simpler plastics, to where we are now, is now that we have these composites, these thermoplastic matrices, we're competing against steel, aluminum, things of that sort, because of the strength and stiffness. So this is shifting the conversation from, a lot of the times what we hear, the common perception is toys, right? These visual objects. And now we're talking about actual tools, things that can have end use, things that can be evaluated in real test cycles. And so that's where these different fiber options start to allow us to have that conversation.
Yeah, exactly. And it looks like we have a few questions coming in. And so we'll start to answer these as we go through. And that way you guys can ask as you want. And then when we see fit, we'll start to answer. So it looks like we have one. Is it possible to vary the percentage of fiber and matrix percentages while printing? And so this is a really good question. Adam prints a lot in our composites, so I'll allow him to take this one.
Yeah, so I can't speak to what other companies are doing, but I can tell you here at Markforged, you have the ability with our Eiger slicing software to dictate not only the percentage of fiber reinforcement, but where it goes, where it's pathed in each Z-slice layer, whether it's concentrically pathed, as these 2 examples that Nick's showing off, around the walls to add strength to the perimeter, or we can also path an isotropic panel. So that's going to be a full fill per the Z slice. And so this allows us to be really specific. We cannot adjust the actual thermoplastic blend. So this is like very important to go back to that distinction of the thermoplastic, the plastic matrix itself is set. That's a material that we extrude as a filament in our FDM style printers. But you do have the ability to kind of, at a very finite level, control the continuous fiber reinforcement throughout the part itself.
And this brings up a really interesting differentiation between 3D printing composites and traditional fiber layups that you may do. So for example, if you're doing a carbon fiber layup, you put the actual reinforcement into the shape that you want, and then you may paint the matrix over it, whether it's some sort of polymer or some sort of epoxy, and you're really fixed on like you're using carbon fiber, right? And so you buy that really expensive fiber and then put it into the shape you want. Whereas with 3D printing, it brings up this interesting point of, okay, I don't necessarily need isotropic strength. I'm having bending in this direction. For example, this is a soft jaw, or half of a soft jaw. And this is going to be experiencing bending in this direction. So the concentric fibers make a lot of sense. And so it brings up, there's this whole new world of utilizing those material properties and then thinking critically about how that fits into the loads that your part is going to be experiencing. And so now we're not as much talking about, all right, I'm going to print this part out of ABS and like it has this purpose of like looking nice. It's like there's all these different avenues you can be thinking about the materials, about how the material acts, how you actually place the material in the part.
Yeah, so it kind of, as Nick is speaking towards, it's not this universal application of reinforcement as you would do in a traditional layup or something of that sort. It is very specific to the point where we can control the direction of the fibers as well to respond to very specific loading conditions. And that's kind of where we separate ourselves. And the other part of that question, I apologize, is matrix percentages. Yes, so we also have the ability to control the density of our plastic matrix. So that'll impact cost, that'll impact print time. But depending on what your needs are, we can modify our prints via our slicing software to do that.
Yep, certainly. And just to give a picture, this is reinforced with Kevlar, that yellow filament, and this is the first few layers of this part here, which is an robot end effector. Let's see. So it looks like we have a couple more questions. So one question is, why is PEEK and Ultem so popular in the aerospace industry compared to polycarbonate or nylon and others? So there's a couple reasons for this. One is that similar to nylon, PEEK and Ultem are extremely chemically resistant. And so that's really good for use in a machine shop, where a lot of times companies are machining PEEK or Ultem. So that's one reason. And then its heat resistance is another huge reason, despite its strength and stiffness, which we've mentioned heavily. It's a plastic that can really resist pretty much the most heat out of any other really accessible plastic out there. And so that makes it really ideal for the aerospace industry. Whereas polycarbonate is like similar to PEEK and Ultem. It's just like PEEK and Ultem mini. Like, it's not quite as good in like everything. It's like got pretty good heat resistance, got pretty good strength and stiffness, but it's not quite on par with PEEK and Ultem. And then nylon, while it does have good chemical resistance, as we said, its strength is not quite up to par.
Yeah, so another huge priority for aerospace specifically is the ability to be self-extinguishing. Mm-hmm. And so that's where PEEK and Ultem are going to be definitely more close on the spectrum to V0, which is the rating scale. I don't want to speak towards all. I'm saying they're all V0, but that'll allow the aerospace industry to be more confident in using those materials over, say, some other composites or thermoplastics.
Yep, certainly. Let's see. One question, do we have papers comparing the mechanical characteristics of 3D printed parts with our filaments and printers compared to traditional carbon fiber? That's a good question. So one thing I'll say right off the bat is our continuous carbon fiber filament is weaker than a traditional carbon fiber layup. You can get strength that's almost comparable to steel with a really good carbon fiber layup. Mm-hmm. And what we're seeing is with our carbon fiber material specifically, we're getting close to basically like the yield strength of aluminum.
Right.
And then you keep in mind that you're reinforcing parts with that carbon fiber. So that part is not going to have 100% the strength of carbon fiber, but it has that reinforcement in it. So one thing that I like to tell people is that we make parts that you can replace aluminum parts with. Their strength, you can get to the point where, depending on your application, you're able to have it strong enough to replace aluminum, which is not as strong as a carbon fiber layup.
Yeah, and I think strength is always just one part of the conversation, exactly. Right?
Yes,
that's one material property that we can focus on and steer this entire conversation about. But the other benefit of using these plastic matrices is that we're reducing weight. So as we were talking earlier about carbon fiber, continuous carbon fiber reinforcement is that strength to weight ratio. So we're dropping the weight, which is then making the part more ergonomic, whether it's a user that's lifting or kind of picking this part up constantly throughout the day. It could be a robotic arm. It could be in a manufacturing line, whatever. We're seeing that the number of cycles that we can put on our printed parts, even if it's not matching the overall strength as that one property, that weight reduction also has benefits. So there's kind of trade-offs throughout the conversation when we're talking about different material characteristics. And
it's interesting that we hear questions about how does it compare to a traditional fiber layup? Right. And often we see that our parts aren't really competing with traditional fiber layups in terms of their applications. A lot of times when you actually choose to pay the money for making like a carbon fiber part, the traditional way, it's actually pretty well suited for that application. And what we see on the flip side is we're replacing aluminum a lot of the time because of that weight reduction, and that if we're talking specifically strength in a factory setting.
Sure.
Let's see what else we got. So this is a good question about the anisotropic behavior affecting the mechanical properties in 3D printed composite samples. So that's a very good. So you mentioned that we do have this isotropic fill that you can do with fibers, but really it's a quasi-isotropic fill because it gives you equal strength, essentially equal strength in those two bending directions in the XY plane. But when it comes to the Z direction, as you have with the thermoplastic printed parts and composite printed parts, the Z layer adhesion is a problem that's run into a lot.
Right. So, yeah, as Nick alluded, we are still limited by the style of printing that we do here at Markforged. It is still an FDM style. We are still depositing this thermoplastic in the XY plane. And the XY strength, or excuse me, the Z strength is about 70% of that XY. So we are always still going to be talking about interlayer adhesion, and that is a part of the process. But that's once again, by using a nylon 6 base in our plastic matrix, we have really stable prints. The abilities and capabilities of our printers to print at the kind of print height resolutions that we're capable of getting down to, in some cases 50 microns, that allows us to limit any kind of interlayer delamination or shear stress when we're talking about different applications.
Yep. Let's see. Oh, looks like we have a customer making a comment. As a user, I would also like to add that it's a huge benefit with Markforged parts to embed metal parts for extreme cases of added strength, such as printing custom nylon or composite features around a steel rod. And this brings up a great point that I did want to bring up, especially when we're talking about like Z strength or Z layer strength, where yes, you're always limited by the tool that you're using to manufacture something. Not everything is the perfect manufacturing tool.
Sure.
But mixing 3D printing with other established manufacturing methods and using intelligent mechanical design is always something that we're big proponents of, and we say this almost every episode. It almost always comes back to this, where it's you want to be mixing those off-the-shelf parts, like a steel rod, for example. Even on our metal printer, it doesn't make much sense to print a steel rod when you can buy it off the shelf. And then integrating that into your 3D printed parts to make these assemblies that are optimized for your use case.
Sure, yeah, and my favorite when it comes to that conversation, which I really appreciate this comment, is talking about printed threads, right? So we have the capability to print plastic threads, but depending on how many times you intend on threading in that mechanical fastener or pulling it out, those plastic threads that we print are going to degrade at the same rate of any other off-the-shelf plastic thread. So we always recommend using a heat set insert, which is going to kind of allow you to have this thread engagement that is constant. It's going to come at a fraction of the cost, and your kind of yield or overall success of the printed part is going to extend dramatically by using this cheap off-the-shelf component.
Yeah, and it's similar to manufacturing any other part if you're doing it in a traditional way, right? If you're going to machine an aluminum block or out of an aluminum block, and that part is going to be part of an assembly, you're not also going to machine bolts for that assembly. You're going to buy those off the shelf. And so it's introducing those same methods you're already using in other manufacturing methods. Looks like we have a question on when will ESD plastics be available? That's a great question. I don't know the answer to.
Yeah, I'm not sure either. We're always looking to develop additional requests or needs to meet the applications that we're seeing in the field. So.
Yeah, certainly. But that's definitely an interesting use case. Question on, will you ever be offering a metal printer? We do currently offer a metal printer. You can also, another thing to check out on our website, although we're more focused on composites in this discussion, also check out, if you're interested in our metal printing, our other AM Friday episodes. I'm pretty sure episodes 1 through 4 were all about metal printing, and those are on this YouTube channel. And so you can check those out. But yes, for those of you who may not know, we offer a full metal system. So that's the Metal X printer, which comes with the washing station and the sintering furnace, which is the full system that you need to be 3D printing metal parts. And so check out our other AM Fridays to learn more about those. So this is a really good question. This is a question we get all the time. Aluminum versus 3D printed, price on a custom part. And so our favorite, do you want to say it together? Our favorite phrase to say this is, it's geometry dependent. And so Adam, if you want to talk a little bit to this.
Yeah, I mean, so it 100% depends on the features of the part, like the cost of milling a pretty straight aluminum block versus printing the part. We're likely not going to be competitive, but as that complexity increases, complexity in 3D printing doesn't come at an additional cost. All we have to do is take that solid part file and slice it in our slicing software. And that's when we're starting to see the kind of economic argument made that when we're talking about more complex parts that take a lot more fixturing, tool up time, engineering on the front end to produce in aluminum, we're typically coming at a tenth of the cost, somewhere around there. And so that's when it kind of makes our jobs easy. The printers kind of sell themselves at that point, where It's a hard value proposition to argue against when we're seeing similar strength and stiffness requirements of, say, a 6061 aluminum versus our Onyx reinforced 3D printed part. But at a tenth of the cost, that kind of ROI, that return on investment is really easy for us to develop as a team here.
Yeah, and you bring up that the more complex the geometry gets, the more it makes sense to 3D print the part out of that high strength plastic, which is interesting because it's always this mantra of like, you get complexity for free with 3D printing, which is largely true, but there's some caveats to that, of course. But the biggest, in my opinion, as a mechanical engineer, advantage I see is you don't have to deal with CAM. And CAM was like the bane of my existence when having to design parts to be machined on a mill, because you have this part that you want, and then you get into CAM and you're like, I have to make all of these trade-off decisions on how fast I want this to be produced and how accurate I want it to my actual design. And so, and not to mention that skilled labor that you're putting into the planning process for actually making the part. And so being able to skip that CAM process where you can design the part and then you throw it on the 3D printer to print, overnight or however long it takes, it skips that process, which really increases that efficiency, not to mention the iteration speed and the cost of that part.
Yeah, and I think the other kind of side of that coin is we're no longer talking about like tool head clearance and clashing along the part,
right?
Which is a big part of machining. Whereas in 3D printing, that's not a factor. That's not a design limiting parameter that we have to kind of design around. So yeah, it allows us to have a lot more design freedom. As Nick said, it kind of accelerates dramatically the design cycle. It allows us to prototype multiple iterations rapidly versus machining. You maybe get 1 to 3 shots, depending on what your budget is for that part, to get it right. So it completely changes the game.
Yeah, and so that's that question that Mark said, aluminum versus 3D printed price on a custom part, is really the central question that we like to explore in our jobs in terms of like what application we're looking at and how you can really optimize for that. So that's really a central question of what we do. So it's a very good question. Let's see. I'm not sure if I understand what this question is asking. Do you see stiffening of plates/shells a way to increase carbon reinforced element strength?
Yeah, so if I'm understanding this correctly, this is about kind of fiber reinforcement strategy. So the benefit with our printers, the continuous fiber reinforcement and the ability to selectively place it either as a concentric ring, as we talked about earlier, or as an isotropic panel, allows us to deliberately place strength or stiffness in portions of the part. We can go even further to talk about kind of beam bending theory, but the idea is our fibers act strongest when they're in tension. So depending on what the loading condition is, we can add these sandwich panels, as we like to call them, of fiber that resist the bending arm or the bending moment. Similarly, if we're getting more of a uniform loading condition across the entire part, we can create this shell of fiber reinforcement, which then allows us to responsively add strength to the overall part.
Yeah, and if you're interested in learning more about how to reinforce parts and this sort of design of composite printing, there's a lot of good resources on our website as well. We have a composites design guide of how to design for our printers specifically. And also there's a couple of good webinars and videos on there about what advantages does this continuous fiber really offer and how do you best utilize that. So definitely check us out on that one. We have a question about interested in buying one of our desktop printers. So I would point you to getting in contact with our sales team on our website if you're interested. That's markforged.com, and there's a bunch of places there that you can get in contact with our sales team if you are interested in either purchasing a printer or learning more about it. All right, and again, if you have more questions, continue to put them in that chat box. It looks like that was the end of them. But I think one thing that we can continue to talk about is we sort of got into what each fiber is specifically advantageous for. So we talked about carbon fibers is the stiffest and strongest, but fails catastrophically. Kevlar is good for being pretty durable because it's got that ductile property. So it's something that fails more slowly, I guess, as you could say.
Yeah, and Kevlar is going to be better for like a repeated impacting or repeated loading cycle. So that continuous impact Kevlar is going to be more resistant. It's going to be more durable, which will allow it to kind of take that abuse. Versus say something like fiberglass, it'll be better in an application where there's intermittent loading. It's not going to kind of deform in the same way that Kevlar is. So it'll bend, it'll flex, and it will more than likely come back to shape, but not in the same way that Kevlar would if that loading cycle is kind of in that repeated motion.
And so one specific application here is end effectors, where you're seeing them come into contact with production parts repeatedly or tools very repeatedly. And so as I mentioned, this end of arm tooling here is reinforced with Kevlar, and that's one really good use case for it. And then this soft jaw happens to be reinforced with fiberglass, and as we mentioned, really depending on how hard this is intended to be clamped, fiberglass and Kevlar can both be really good options for soft jaws.
And I would say carbon fiber probably is still the most common fiber we use here. It does have that highest strength ratio. It does have the highest, or close to the highest stiffness. And so more often than not, when people really want to compete with these aluminum parts that we talked towards earlier, that's what they're going to go with.
It looks like we got another question. Practical heat ranges for Onyx parts. So this is a really interesting question. I can give you the short answer, which is the heat deflection temperature of Onyx is 145 degrees Celsius, which is around 300 Fahrenheit. But that doesn't really give you the full picture, because that basically, the heat deflection temperature, if you're not familiar with how it's measured, they basically take a beam and they slowly increase the temperature and they deflect it. And once it reaches a certain percentage of deflection, that's the heat deflection temperature. And so what this does is it, in my opinion, unfairly gives advantage to really stiff materials, because, for example, nylon has an abysmal heat deflection temperature, partially because it's not very heat resistant, but also partially because it's a very ductile material. It's a very flexible material. And so that low stiffness makes it so it deflects to that point very quickly, regardless of if the temperature is high or not. So with that rant out there, so Onyx, for example, we're seeing around 300 degrees Fahrenheit for heat deflection temperature, which, is like a decent guideline for like a ballpark of where that operating temperature can be. But we see Onyx parts used in welding fixtures, in thermoset molds and stuff like that. So you might be able to see temperatures that are actually higher than that for really short spans and not see your part really be destroyed or really plastically deformed.
And that's where kind of the last fiber that we didn't talk about as much is that high strength, high temperature fiberglass that allows us to increase that heat deflection temperature. So once again, the whole goal of using composites is taking the advantages or disadvantages of the base plastic matrix or thermoplastic, and then adding in these specific fibers that have within themselves specific characteristics that allow us to then increase whatever our needs are.
And it's interesting. Reinforcing with the fiber also solves that HDT problem that I was mentioning, where it increases the stiffness of that part. So even if you're getting to an operating temperature where that Onyx is beginning to lose its strength and stiffness, reinforcing it with the fiber gives it that extra stiffness to keep it from deforming at those higher temperatures. So let's see. Could you briefly discuss design and process validation approaches to check that the printed part achieves desired mechanical properties?
So as an application engineer,
this is Adam's wheelhouse very much.
At Markforged, this is kind of where I live. So there's kind of a couple answers to this. The most standard process in the industry right now would do some sort of FEA analysis to confirm that the printed or manufactured part matches anticipated digital properties. Unfortunately, that's something that we're still kind of looking into ourselves here. And over time, we will get closer and closer to having FEA analysis. Unfortunately, we don't have it right now. So the recommendation that we always make is take the printed part. We'll work with you to develop a benchmark part, to engineer it to the application needs and requirements, and then put it in the standard loading cycle that you're putting your aluminum or whatever material part in today. More often than not, we're seeing that we're meeting the loading conditions, and if not exceeding them. And that's one of the easiest ways for us to confirm it. If you would like to have a better idea of, say, accuracy and tolerance on some of our industrial machines, we also offer via our laser micrometer some laser scans. So you can pause print, mid-print, as some of these kind of cutoff prints that we have, do a scan of the printed part, and then compare it to the digital file of that specific Z-slice and measure how far, how close we are within the certain tolerance spec. So that's a little bit kind of different than the mechanical properties, but that'll allow you to at least understand kind of how we're doing on certain tolerances and things of that sort.
And I'm very excited to see how FEA analysis, or I guess that's redundant to say, how FEA starts to work its way into the 3D printing world, because FEA comes from this concept of homogeneous parts, really, right? And so doing that sort of complex analysis on a part that not only has multiple materials in it, but also has an infill structure, and then a different structure that the continuous fibers are routed in, it makes it a difficult problem.
Right, and that's where we continue to commit resources and look into it.
Yeah, I'm really excited to see really where the 3D printing industry in general goes towards having that hardcore analysis of those parts, especially as the aerospace industry, which we know highly regulatory, begins to adopt more 3D printing technologies.
Right.
All right, so we have a question on mixing Kevlar and carbon fiber. We actually do get this question a lot, and the answer is no, you cannot. You can only print in one fiber at a time. And that's a really interesting question, where I do see you could get some marginal advantages in where you may want certain parts to have certain properties, but I'm sure you deal with this question a lot. Can you speak to it?
Yeah, so recently we've been doing some kind of internal testing around this as well. As Nick said, the way that our printers are set up, you can only select one fiber at a time to print in one part. But similar to the point that someone brought up earlier about using mechanical components, we can treat a second print in a way as its own mechanical component, right? So we can leave a cavity or a space within a part, and then say print the entire part with Kevlar reinforcement, and then print a bar printed with carbon fiber. If we understand that having that stiffness in a certain axis will give us benefits in the application, and then we can combine the two. We can insert that carbon fiber bar into the part, so long as we've designed around it that way. And it's something that we've been kind of playing around with to see if there are benefits. Right now, it doesn't seem like there's a strong enough need from the applications we're working with to possibly consider an additional fiber head or an ability to switch mid-print. But this is a workaround that we have ourselves kind of tested and trying to see if that adds any benefit to the parts themselves.
Certainly, great. Let's see. Another question on what plastic the Onyx filament is made of. As we mentioned, it's a nylon 6 mixed with chopped carbon fiber.
Chopped short strand.
Short strand carbon fiber. Exactly. Oh, okay. So we had a question. This one's interesting. What are some current limitations of FDM style carbon fiber based printing? What can be improved, and what does the future look like?
Wow.
That's a great question. So I think we've mentioned a couple of the limitations already, and we can dive a little deeper into that. So one limitation, as we mentioned, is you don't have full isotropy. And so that, while there are some applications where you really do need that isotropic strength, with FDM style printing in general, you almost always have that difference in that Z-layer adhesion compared to the strength of the actual material. So that's one, although a minor downside does exist. And then the other major one that I see, and by major I mean like really worth mentioning, is that it's slower to print with continuous fibers. And so for a lot of customers, that doesn't matter at all, because they're looking at, I'm skipping a 6-week lead time from the machine shop, and like a day-long print is not an issue to me. But some people, especially those who have the preconceived notion of 3D printing where you get parts on demand, it's a little more shocking to them that you may have a part that takes a day or so to print. And so laying those fibers is a really intricate process, and so it takes a little more time to print those parts.
Yeah, I mean, I'd agree with those. And also just kind of some previous problems that we've already overcome were, the print bed adhesion, the differential cooling across parts, support structures. There's been a lot of different approaches within FDM style prints of soluble supports, tearaway supports, which we support, things of that, different design limitations of bridging lengths, overhang angles, things of that. As an industry, we've made pretty big strides in overcoming those. I think Nick's, really intelligently kind of keyed in on the last few that we're looking at of interlayer adhesion is always going to be a concern when it comes to FDM style printing. It's part of the process. I'm not sure if there will ever be, short of a post-processing solution, a means of fully overcoming that, and then print speed itself.
Yeah. And one thing that's not as specific to Markforged in terms of those filled thermoplastics and those mixed thermoplastics is surface finish has been something that a lot of companies have been tackling, and us included, and I think that we've really gotten to a good solution on is how do you first off design the material to have a really nice surface finish, and then how can you make your printing process conducive to making a high strength part that doesn't feel like you're getting carbon fiber splinters.
Yeah, I think I continue to be amazed with the surface finish here, and I can't tell you how many events or trade shows that we have people come up to us and say, you must have sanded this, you must have post-processed this in some way, because I think a lot of people that are used to FDM are used to seeing those Z registration lines, that kind of evidence that it was printed on that style printer. Unfortunately, with our ability to get down to those 50 micron layer heights, we're able to overcome that.
Cool. Let's see. Another question on mixing materials. I feel like we touched on that pretty well. Okay. This is an interesting question. What programs do you recommend for design? Does Markforged have its own software to place carbon fiber? So this is kind of like a two-part question. The first part is, what do we recommend for designing? I've used a few different CAD softwares, and honestly, I grew up in my engineering life using SolidWorks. And I've been using Fusion 360 recently, and I think they're both powerful tools, and they both have their advantages and disadvantages. I would say in terms of 3D modeling, you should use what you're most comfortable with in terms of like if you're an engineer and have experience with it already. I don't think designing for our printer, any of those specifically have advantages that makes it easier. You should really use what you're comfortable with is what I would say.
Yeah, for us specifically, as long as you have the ability to export an STL file type of high resolution. So regardless of how great our slicing software is, if you export a low resolution STL file, then your print is going to look low resolution. It's going to be faceted. So as long as you have the capability to export a high resolution STL, I agree with Nick. Whatever you're comfortable with. We also use Onshape as well. So there's
a bunch of really good tools out there for sure. And then the second part of that was, do we have our own software to place carbon fiber? So Adam, you can speak to this a little bit if you would like, but we have a cloud-based software that's called Eiger, which I cannot say enough good things about it because I've used a lot of different 3D printing softwares, and Eiger I really love. So you can take it away if you'd like.
Yeah, I mean, I would encourage you to just hop on our website. You can download a free trial, pull one of your parts in, and start kind of slicing it and see what the capabilities are. I agree with Nick. I can't say enough good things of how intuitive and easy it is to use to kind of specifically place fiber wherever you need it. And
there is that learning curve because now you're not mixing two materials together, but you're using two materials at the same time for specific application purposes. And so building that skill is something that definitely happens as you start to use the software. But what I really love about it is there's the internal view that you can go into when you're starting to place fiber, where you can look at the part layer by layer, and you can decide how you want to route fiber in each individual layer of the part. So if you want that granularity, you can have it, but then also, you can just highlight multiple layers and build a sandwich panel within the part or something. So it offers you that freedom of picking specifically how many fibers and where you want them placed, and doing a more general approach to it. And so I think it's an extremely powerful software.
Yeah.
All right, let's see. We get this question a lot as well. Machining onyx. So definitely something that I don't recommend to people. But Adam, you have more experience with this question.
Yeah, it's not impossible. So because we print with a plastic matrix that has an infill density, what I would encourage is if you need a critical dimension in a plastic part, specifically of ours, then you have the ability to increase the number of walls that you're shelling your part with. So if that is the approach that you need to take, then we would just recommend accommodating in our cloud slicing software Eiger to do that. So you would just increase the number of walls, which will have a small impact on print time, not dramatic, which should allow you to machine down to whatever critical dimension you need.
Yeah, and it's interesting. Often people, their notion of how accurate 3D printing can be is actually off of what current day industrial printers can achieve, including ours. And so people are often thinking, I'm not sure how high precision you want. There's definitely, CNC machines out there that can achieve higher precision than our printers. But a lot of people come to us, they're looking at the order of like 10 thou or 5 thou precision, which we're really starting to approach with 50 micron layer heights. And then, the XY precision might not be quite up to par with that, but we're really starting to see accuracy and precision that's on par with the kind of the standard for CNC milling in like a non-precision, like super precision.
Yeah, so as Nick's saying, we're close. So in the XY plane for our composites, we're about a plus or minus 125 microns. And in the Z plane, we're within a layer height. So depending on 50 micron, 100, 125, depending on your fiber reinforcement, we're getting close to the industrial grade tolerance needs.
And if you take 125 microns is around like
it's about 5 thou.
5 or 6 thou, yeah. So we're really getting down to that. So depending on how precise you want it, machining may not even be something you have to do.
Sure.
All right. My computer just died, so I don't know if there's more questions that came in.
There are a few more coming in. I think we'll do our best to kind of answer these last few, and if then there's any questions we don't get to, we'll definitely kind of either respond to you or please kind of come to our next session and continue to ask questions.
Yeah,
go to our website, whatever needs you have.
And we also, before you start, next week, we're going to do a sort of mailbag episode. So I think we're going to send out a link for you to fill out questions, more like high level questions on 3D printing and the 3D printing industry to send to us. And then Daniel and I next week on Friday are going to be piecing through those and answering some of those really thought-provoking questions. So there's going to be a way for you to ask more through there as well. So
great. Yeah, so I'll read through these last few here. We have a question that mentions interlayer adhesion as a limitation. And can preheating previous layers help diffusion of carbon fibers and possibly result in more strength? Has Markforged explored into this? Not to my knowledge.
Yeah.
So our heating per layer is constant throughout the print. We're not looking at differential temperatures, feed speeds, things like that. The more we keep that constant, then we can have a more repeatable, reliable print. Not saying that it's not a viable approach. It's just not one that we've possibly explored to date.
Yeah, and an interesting addition is you're really looking at starting to have like a heated chamber. If you're trying to keep those layers from cooling and creating that Z layer adhesion problem. And so then you start to have this like really highly controlled environment that becomes very expensive. And so it's that, although that is a small issue that is with the FDM style prints, it's kind of like an accepted limitation as we work on other parts of the printer to keep it at an affordable price, really.
Right. Next question here. Any intent of adding dissolvable support material capability? I mean, I'd say nothing's never out of consideration, but at the moment we don't offer soluble supports. When can we control reinforcement regions in XY plane of parts, i.e. reinforce left half of a part? So this is, I'm assuming coming from somebody who's currently using our product, is when you're reinforcing a Z-slice layer, it's a uniform or universal application of those different fiber reinforcement parameters. So if we're gonna shell that Z-slice layer, it's gonna apply a shell across the entire part. You do have the ability to select, though, for concentric fibers, just the exterior, the inner holes themselves, or both. Versus isotropic is gonna give you a laydown of fiber across that entire Z-slice. Once again, it's something we're not currently doing, but nothing's out of the possibility. Yeah,
and definitely check out, there's some caveats to that as well that you can check out in our composites design guide as well.
Sure. I got a few more here. Any ways to have parts printed from your systems for, say, a university project? Love the Onyx sample I received and would love to use it towards a senior engineering project. So I think Nick mentioned earlier, I actually run our test benchmark farm here at headquarters. If you're interested in using our printers, purchasing our printers, please reach out to our sales team via our website, and they'll be happy to put you in touch with someone like myself, and we can talk about trying to get you some test parts. What is the most complex or best part you have seen being printed on a Markforged printer?
More opinion question. I kind of like that.
It's a tricky one.
I think we have a ton of parts that our customers are printing. It's probably going to be hard to choose, but since we have that mold there on the desk, maybe you could talk about that.
Yeah, sure. So this is a part I do like very much. So as I mentioned, this is a thermoset mold from Humanetics, and they're a leading manufacturer in in crash test dummies. And so this part's really unique. Number one, because it's a functional thermoset mold, which is awesome. And number two is if you compare the price of this to actually machining it out of aluminum, it's like it doesn't look that complex to you. I don't know if you can see it from there, but it's really the fact that the neck ring is like a three-dimensional shape, right? It's got these steps upward here, and then it's got complexity in all directions, which is what makes it really hard to machine. So this is one of those cool use cases where it's not a really flashy, complex geometry, but it's a geometry that is very hard to machine out of aluminum. And so by printing this instead of machining it, it's literally 2 orders of magnitude cheaper. It's 1% the cost than if compared to their quote of actually machining this thing, which is really cool because it's not one of those things where it's got like all these undercuts and like all this crazy. You just have to machine it in multiple orientations.
Yeah, I mean, I think the more blanket way to answer that too is literally pick an application, and we're probably doing something with them right now, which is I think the most exciting thing for us here at Markforged is that we're touching so many different industries with these industrial grade 3D prints, and I think. I'm continuing to be excited about where we can go with it. What's the next application we're going to see coming in the door? So I think we have one last question here. We'll take this one and then we'll kind of sign off for the day. So this one is, what about the delamination effect during drilling of 3D printed continuous fiber composites, especially during the tool entry and exit? So the benefit of how we how our algorithms slice your solid part is that we will always place concentric rings or walls around any hole features. So that's going to give you some stability if you need to drill for that tolerancing that we were talking about earlier. That'll give you the stability to make sure that you're not seeing any delamination around that hole itself. As I recommended, if that is the approach you are taking to get down to a critical dimension, I would always push you to maybe increase the number of walls that are there by default. But I have seen little, if any, delamination during drilling processes.
Cool.
All right. And with that, I think we're going to bring today's AM Friday to a close. Thank you all for joining us today. As Nick and Adam mentioned multiple times throughout, you can visit us at markforged.com, which is our website that we are constantly developing. So we have a team that's dedicated to adding things to the website. We have a Learn section where you can learn more about some of the things we talked about today. You can also download data sheets to get specific specifications on both the materials and the printers. And you can also sign into Eiger, which is our slicing software, as we talked about today, and upload your own parts and see how you can reinforce them with fiber. We do these AM Fridays just about every Friday now, so expect us here next week as well. We will be sending out a survey if you're signed up to receive our emails to get some questions in advance for next week, so we can try that out a little bit. If you're not signed up for our emails, you can do so by visiting us at markforged.com and finding the newsletter sign-up form, which you'll see on the homepage if you scroll down. Otherwise, you can subscribe to us on YouTube. And you can reach out to us on the various social media platforms that we're on if you'd like to submit questions that way. Again, thank you all so much for your questions and your comments and engaging with us today. We hope you enjoyed today's AM Friday, and we hope you have a great rest of your Friday and a wonderful weekend ahead.